All right, guys, here is the second part of the Chapter 9 slides. I did the first video. I did a few too many hmms and ahs and pauses, and I went a little too slow. I'm going to try to go a little faster through this one. We'll see if it works. So, quick review of what we did last time. What is our formula for work? So, I'll give you a little pause. Try to remember that one. It is work equals the magnitude of force times the magnitude of displacement times the cosine of theta, the angle between them. Or if you're feeling lazy, just work equals FD cosine theta. Second question, what are the units for work? Do you remember the picture of the old guy with the beard and the comb over? His name was James Prescott Joule. So joules are the units for work. And his third question, is work a vector or a scalar? Well, look, work is hatless. If you're not wearing a hat, you must be a scalar. So now we're going to talk about energy. Energy is the ability to do work. There's different ways to define energy. We're going with this one. You have mechanical energy. This is the energy due to the movement of something or energy due to the position of something. This is different than other kinds of energy like chemical energy. Heat is another kind of energy, which ultimately those are mechanical energy way down at the atomic level and things like that. And you also have, well, E equals mc squared. There's energy related to mass. That's a different thing. Take physics too. I'll teach you all about that one. But mechanical energy. There are two forms of mechanical energy, kinetic energy and potential energy. We've been teaching you about these things throughout your entire academic career. So think of the roller coaster at the top of the hill. That's got potential energy. It's not moving, but it's about to move. So that's potential energy. Once it starts going down the hill, it has the energy of motion. That is kinetic energy. And energy, just like work, is a scalar quantity. And just like work, its unit is J for joules. So this slide, where we quickly go over the quantity, symbols, units, and vectorness of these things. So you have work. Its symbol is W. That's very good. Its units are J for joules. Work is a scalar. And then you have energy. Its symbol in general is going to be E without a hat. E with a hat is the symbol for electric field. Take physics too. I'll teach you all about electric fields. And we're going to have different kinds of energy, and they'll all have their own symbols. Its units are also joules, J, and it is also a scalar. And there will be all different kinds of formulas, as you'll see, for the different kinds of energy we're going to deal with. So first we'll deal with kinetic energy. Kinetic energy is the energy an object possesses due to its motion. It seems kind of like momentum, but it isn't. It's very different. Momentum is a vector. Kinetic energy is a scalar. Momentum is directly proportional to velocity. Kinetic energy is proportional to velocity squared. So if you're looking at this formula, Ke, our symbol for kinetic energy, is equal to 1/2 m times v squared. So being proportional to v squared, you also say it has v squared. It's directly related to v squared. Means that if your velocity goes up, your kinetic energy goes up by a lot. Because if, for example, your velocity doubles, your kinetic energy goes up by double squared, which is 4. If velocity goes up by a factor of 3, kinetic energy goes up by a factor of 3 squared, which is 9. So remember that unlike momentum, energy is a scalar. So if you're going to the east or if you're going to the right, you have momentum to the east. If your kinetic energy in that situation is not going east, it's not going to the right. It has no direction. So if we look at this picture here, we've got a cheetah chasing a gazelle or some other kind of ungulate. Both of them have mass, both of them have velocity, therefore they both have kinetic energy. So what is the kinetic energy of a 40 kilogram cheetah moving at 20 meters per second? So just plug the numbers into the formula. 1/2 times 40 kilograms times 20 meters per second squared will give you 8,000 joules. So when you're doing this in the calculator, make sure you're doing it carefully. Notice in the formula, only the V gets squared. So don't do the whole thing and then square the whole thing. Just square the last thing. So in your calculator, you could hit 0.5 times 40 times 20 and then the squared button. That'll do it. Your calculator knows the order of operations. If you do it that way, it knows you only mean to square this last part here. So you get 8,000 joules. So if our 40 kilogram cheetah is moving at the same speed, but in the opposite direction, is its kinetic energy going to be 8,000 joules or will it be negative 8,000 joules? So think about that for a second. Is it going to be 8,000 joules or negative 8,000 joules? The answer is 8,000 joules. Energy is a scalar. Direction doesn't matter. So the fact that you're going in the opposite direction would mean that you have opposite momentum, but we're not worried about the momentum. You would have the same amount of kinetic energy because it's a scalar. Direction doesn't matter. So besides kinetic energy, we also have different kinds of potential energy. We're going to learn two for our class. This is energy that has the potential to do work. So in college, and I don't know why this is, you may see potential energy written as a capital letter U. Those of you who are very observant will notice that the letter U does not appear anywhere in the word potential. So I don't know why we use U for the symbol for potential energy, but sometimes we do. I'm not going to do it that way. I'm just showing you this in case you ever see it in your future physics studies. So we'll start with gravitational potential energy. Our symbol for that will be GPE. So GPE is equal to mgh, where m is your mass in kilograms. G is the acceleration due to gravity. You'll use the positive number, positive 9.8 meters per second squared, and h is your height in meters. So what would be the GPE of a 2 kilogram physics textbook held a height of 1.5 meters above the ground? Well, take your formula, plug in your numbers. 2 times 9.8 times 1.50 gives you 29.4 joules. Very easy. And the last kind of potential energy we're going to deal with is called elastic potential energy. It is also sometimes called spring potential energy. I'm going to call it elastic potential energy, EPE, though other people would write this as SPE, but I'm going with EPE. So this is the energy of a spring or anything that is spring-like. So it can be an actual spring, it can be a rubber band, it can be a bungee cord. It can be, if you're into archery, it could be the energy that you put into the bow when you draw back the string. Sorry. So our formula for this, EPE, is equal to 1/2 kx squared, where k is the spring constant. This is just a number that tells you the stiffness and the strength of your spring. It will have units of newtons per meter. And spring constant, if your spring is very strong and it takes a lot of energy to compress it or extend it, your spring constant is going to be very big. So think of like a giant spring like you might find on the shocks of an old truck or something like that. So a big, thick spring will have a very high spring constant K. And then if you think of a slinky, a very weak spring, that's going to have a very small spring constant K. And X is either the extension or the compression of the spring. So your spring, if you just sit it on the table, wants to be at a certain kind of position. If you stretch it out or if you squish it down, you are either extending it or compressing it. So it is a distance, and the units for X are going to be meters. So let's take a situation. We're going to take a 1.25 kilogram block. We're going to push it against a spring and just hold it there. The spring has that spring constant of 435 newtons per meter, and we will compress it by a distance of 0.125 meters. So what is the EPE, the elastic potential energy? Take your formula, plug in your numbers, do the math carefully, make sure you're only squaring that last number, the 0.125 meters, and not squaring the whole thing, and you get 3.40 joules. It is a form of energy, so its units are going to be joules. So if all of that EPE is converted to KE, if we're turning all of that elastic potential energy into kinetic energy, what will be the final velocity of this block? So if you read that sentence carefully, what that's telling you is all the EPE you're starting with is going to end up in the form of kinetic energy. So this is kind of the baby version of something we're going to learn later in this chapter called the law of conservation of energy. But convince yourself that this sentence here in words is actually saying this. all of the EPE you start with, so EPE initial, will equal the kinetic energy that you end with. So kinetic energy final. So EPE equals your formula for kinetic energy. EPE, remember, is a number we just figured out. So do the math, multiply both sides by 2, divide both sides by m. You've got this. I did the algebra a little bit weirdly here because it's difficult to do algebra well in Google Slides. But yeah, you end up with a velocity in meters per second. So quick review of our quantities, their symbols, their units, and their vectorness. So I will give little pauses as we're going through this, try to play along. What is the symbol for work? The symbol for work is W. Its unit is joules, J. Is it a scalar or a vector? It is a scalar. What is the symbol for kinetic energy? The symbol for kinetic energy is Ke. Some things just make sense. The units are joules. And is it a scalar or a vector? It's a scalar. The symbol for gravitational potential energy is GPE. Its unit is joules. If it's work or energy, its unit is going to be joules. Is it a scalar or a vector? It's a scalar. Again, energy and work are both scalars. Then we get to elastic potential energy, EPE. So its symbol is, I just gave you the answer, it's EPE. Its units are joules. Is it a scalar or a vector? It's a scalar. Spring constant. These last two, spring constant and compression or extension, these are ones students have struggled with in the past. So your symbol for spring constant is K. Think K for constant. We use K for constant a lot in physics. Its units are going to be newtons per meter. Kind of a weird one. You don't actually have to memorize that one, but that's what they are. Is it a scalar or a vector? Spring constant is a scalar. It doesn't have direction. And finally, you get to compression or extension. So your symbol for compression or extension is X. Its unit is going to be meters. It is a distance. If you try to, picture it, show it to yourself with your hands. What does compression look like? You should be indicating some kind of distance that you could measure in meters. Is it a scalar or a vector? Trick question. Because compression or extension is actually a vector, but when you when you square it, you get a scalar. So that's all we need to know for the second part of the slides. Hopefully that helps.